Welcome to qnawire.
This is problem number 3 of the Stewart Calculus 8th edition, section 2.8. Match the graph of each function a through d with the graph of its derivative in 1 through 4. Give reasons for your choices. So here are the graphs associated with this problem. We have graphs a, b, c, d, which are functions f, and graphs 1, 2, 3, and 4 here in red, which are graphs of the derivative of f. And we need to match each graph of f with its derivative f prime. So beginning with part A, here we have this shape of this function, and one of the easiest approaches is to identify the slopes that are 0. Those are ones that are easier to find because a slope of 0 is easily found as a maximum or a minimum, and it could also be an inflection point, but it's clear when you draw the tangent line to that point, and the tangent line is horizontal. So this function here has a minimum with a slope here of 0 at here to the left of the y-axis, and another slope of 0 here to the right of the y-axis. So what this tells us is that the function, the derivative function, will have a value of 0 twice, and only twice, here to the left of the y-axis and here to the right of the y-axis. So if we look at the functions here below, 1, 2, 3, and 4, only one of the functions satisfies this requirement. Graph 1 crosses the x-axis only once, so that does not count. Graph 3 crosses the x-axis 3 times, including the origin, but at the origin the slope is non-zero, so this cannot be the answer. Graph number 4 does not cross the x-axis at all, meaning that it does not have any slopes of 0. Therefore, graph number 2 should be the best answer, and it is indeed the correct answer because the graph of the derivative is not only 0 here to the left and to the right of the y-axis, just like the function, but the maximum of the largest derivative occurs here at the origin. It's the steepest positive derivative, and that agrees here in graph number 2. So we will say and connect graph A with graph number 2, and we match the graph of the function f with derivative f prime in that case. Let's move on to graph B. Graph B seems to have a similar shape, except the main difference here is that there are no derivatives or no slopes with a slope of 0. So that's not easy to identify. Here we have 3 straight lines. One is a positive slope straight line, one is a negative slope straight line, and another positive slope straight line. And what we should note is that when it changes from a positive slope to negative slope, or from a negative slope to positive slope line, the points here are non-differentiable, which means that there is no derivative at these points because you cannot draw a tangent line because these are corners. What that means is that there is no derivative, no defined derivative here at these points. So what we should take away from this function for b is that there's a positive slope, and then it immediately changes to a negative slope, and then it immediately changes to a positive slope. And because of the discontinuity in the derivative graph, we can rule out graphs 1, 2, and 3. Those are all continuous functions. The only function that satisfies is graph 4, because it's the only one with discontinuities. And we clearly see that the graph goes from positive derivatives to a negative derivative or negative slope back to a positive derivative. So B matches with 4. Okay, now on to graph C. Graph C has this shape, and it's a little difficult to identify the slopes here, but one slope we do know definitely is the slope here is 0 at the origin at x equals to 0. At x equals to 0, the tangent line is horizontal, meaning that its slope is 0. So the slope of the tangent line is 0, and the function will cross the origin right here. We see that to the left of the y-axis, the slopes at each of the points are negative, and they're increasingly negative to the left of the y-axis until it gets to 0. And to the right, the slopes become positive. And one more thing we should note is that as we approach x equals infinity, negative infinity towards negative infinity, and as x approaches positive infinity, the function seems to level out, approaching a slope of 0 for the tangent line. So we conclude that the function must cross the x-axis. The derivative of this function must cross the x-axis because the slope is 0 at x equals 0, and that it should approach a slope of 0 as x goes towards negative infinity and positive infinity. And between the two remaining plots, plot 1 and plot 3, the only graph that satisfies this is graph number 1. So graph number 2 is not true. 3, graph number 3 is not true because 3 shows a very large negative slope or negative derivative, or very large positive derivative in the negative x direction, and a very large negative derivative in the positive x direction. And that's not what is happening here. Graph number 1 shows correctly that as x goes towards infinity, the slope, the derivative function, approaches 0. And as x approaches negative infinity, the slope function, or the derivative, approaches 0. And at the origin, the slope is 0, just like it said here. And then we have negative slopes to the left of the y-axis and positive slopes to the right of the y-axis. So graph C matches with graph number 1. Finally, by process of elimination, graph D matches with graph 3, and we can discuss exactly why that's true. Here we have this shape. We can identify 3 clear critical points. There's 2 local maximas here, where the tangent line is horizontal. Here to the left and to the right of the y-axis, the slope would be 0. And then here at the origin, there's a local minimum, and that slope is also 0 of that tangent line. So it'll cross the axis, x-axis 3 times, and this is the only graph where that occurs, graph number 3. And then we see that as x goes towards negative infinity, this function has a very large positive slope. And as x goes towards positive infinity, we see that this function has an increasingly negative slope. And that is also consistent with this graph number 3.